Hello, this video is going to show you the basics of tree automata. Suppose we want to check whether a derivation tree matches the pattern represented by this context-free grammar for noun phrases. We'll say that the root is always NP. Each NP can have a single N child or a left N child with a right PP child. Each PP node must have a left P child and a right NP child. We can implement a tree automaton to check this pattern. A tree automaton is made of four components: a set of states, a set of symbols, a set of final states, and a set of transition rules. We'll start with the symbols. These are the labels of the nodes of the tree that we're checking. For our example, the set of symbols is the set NP, N, PP, and P. Next, we have the states. In our example, we can assign a state for each symbol. We'll call our states QNP, QN, QPP, and QP. Then we have the final states. If the state of the root of the tree is in this set, then the tree will be accepted by the automaton. Otherwise, it will be rejected. Since all valid trees in our example tree pattern have NP as the root, the state corresponding to this symbol will be the only final state. Lastly, we need our transition rules. Each rule will consist of a list of states that is possibly empty, and a symbol. When we traverse the nodes of the tree, we will check the states of the children of each node being read, and the symbol of each node being read. The value that the transition function returns is the state of the node. The symbols P and N are always leaves, so their rules take in an empty list of child states, along with the symbols P or N, and return their respective states. The PP nodes always have a P child and an NP child, so its rule takes the list of QP and NP, along with the symbol PP, and returns the state QPP. Each NP node can have either an N as an only child, or an N child with a PP child, so there are two rules for the NP symbol. One rule has the list with only QN, and the other has the list with both QN and QPP, and both return the state QNP. Now let's see how the automaton defined here processes trees. Our goal is to get the state of the root of the input tree, which will represent the validity of the entire tree. We start from the root and recursively get the state for each child. In order to get the state of the root for this input tree, we need the states of its children so that we can apply the transition rule for the root. We'll start with the left child N. N is a leaf, and we have a rule that returns the state QN when we have an N leaf. Now we move to the other child, PP. We don't have its children's states, so we need to find those first, starting with P. P is also a leaf, and we have a transition rule that returns the state QP when we read a P leaf. Now we move to the other child. We don't have its list of child states, so we need that first. Then we move to the other N node. We use the same transition rule that returns state QN when we read an N leaf. Now we can go back to its parent. There's a transition rule that takes state QN and the symbol NP and returns the state QNP. Now we go back to the NP's parent, and we have a rule that takes states QP and QNP in a list, along with the symbol PP, and returns state QPP. Now we can go back to the root NP. We have a transition rule that takes the list QN, QPP, along with the symbol NP, and returns the state QNP. Now that we have the state of the root, we check if it's one of the final states. It is in QF, so this tree is accepted by our automaton. If this tree had any transition that isn't in our list of transitions, like a PP node with only a P child, the transition function would be undefined, and the automaton could reject the tree. Also, if this tree's root were the PP node, then the tree would have been rejected because the state would have been QPP, which is not one of the final states. The automaton that we just saw traverses the tree from the leaves to the root, which is called the bottom-up tree automaton. Another kind of tree automaton can traverse trees from the root to the leaves. These are called top-down tree automata. For this to work, we need to define the automaton differently. Instead of having a set of final states, we have a set of initial states. This set still refers to the possible roots of the tree, but it's where we're starting instead of where we're going. More importantly, we need to change our transition rules. Here's the bottom-up rule that returns state QPP when a PP node has children with the states QP and QNP. Bottom-up rules like this build the tree by combining child nodes. When we're done, we see if the root is valid. When we go top-down, we start out with a valid state in the root, and as we traverse through each node, we try to build a tree that is also valid. If at any time going through the tree, we're unable to go further because the transition function is undefined for an input, then the tree will be rejected. Otherwise, the tree is accepted. So let's see some of these top-down rules. Each takes a state, a symbol, and a number, and returns a list of states. What this rule means is that if the node we are at has a state QPP, and we read PP, and the node has two children, then the states of those children must be QP and QNP in that order. Let's see some more. Since we have two possibilities for the children of NP nodes, we have a rule for each number of children. If we have state QNP, and we read NP and have one child, then that child has state QN. If we have state QNP and we read NP but have two children, then those children have states QN and QPP. Here's a full top-down automaton for our example tree language. Let's see how this automaton processes the same input tree as before. Our automaton has one initial state, QNP, and we start reading the tree at the root. We have a transition for reading an NP with two children when we are at state QNP. It returns the list with states QN and QPP, and these must be the states of the children. So we move to the first child. We have state QN and read N, and there are 0 children. Since we're at a leaf, we can't go further, so we go back down the other branch. The transition rule for reading a PP with two children when we are at state QPP gives us states QP and QNP. We go to the QP and read the P and see that it has 0 children. Again, we have a leaf rule saying that the list of children is empty. We move to the other QNP node and read an NP with one child. This time, we get the list with a single QN state. We go to that state and read an N with 0 children. The transition rule again gives us an empty list of states because this is a leaf. At this point, there are no more states to check for extending the tree. This means that the automaton accepts the tree. And that should hopefully explain the basics of tree automata. I hope you've gained an understanding of how they can be used to model tree languages. Thank you for watching.